Alright, in this video I'm going to talk about waves and some of the different properties of waves, some of the behavior that waves have that I want you to know about. Okay, so with waves there are two kind of broad class of waves. There's mechanical waves, which require something to travel through, and then there are electromagnetic waves, which are light, which require no medium. And light is something we'll talk more specifically about later, but a lot of things we talk about with waves will also, just waves in general, apply to light. So that's something to just kind of keep back in your mind, that what we talk about waves applies to sound waves, light waves, whatever kind of waves you have. Okay? When you're dealing with mechanical waves, there's two different types of mechanical waves. You can have transverse waves where particles move back and forth perpendicular to the way the wave moves. And then there's longitudinal waves where the particles move back and forth parallel to the wave motion. Okay? So if we look at these two waves down here that are pictured, these gray waves, if you take a look at this first wave, you can see it's getting squished together in certain areas. And so as the wave is going this way, the particles that make up that wave are vibrating back and forth like that. So that's parallel. So this would be considered a longitudinal wave. Whereas in this wave here, as the wave again is still moving this way, now the particles are going back and forth like that, which is perpendicular. So this would be a transverse wave. Okay. When we're dealing with waves, we could talk about single pulses moving down, or we could also talk about a traveling wave. Okay. When we're looking at waves, there's different terminology, ways to talk about the wave that we need to be familiar with. So here is a picture of a transverse wave, and we talk about the amplitude of the transverse wave. This is the size of the disturbance. Waves have crests and troughs. Now, these are interchangeable, really, because if you just look at this wave upside down, it's going to look the opposite way, or if it's not going up or down, but side to side, like which side do you call it the crest, which side do you call the trough. And then waves have wavelength, which is the distance the wave repeats over. And I don't have to measure wavelength in just one place. I can measure wavelength in lots of places. So I can measure it from crest to crest, as is done on this picture. I could also measure wavelength from trough to trough. Now, physicists symbolize wavelength with a lambda. I could also measure wavelength from where it leaves equilibrium heading down to where it leaves equilibrium heading down, and that could also be the wavelength. Okay? Now, one thing that people oftentimes get wrong with amplitude is they say amplitude is the entire distance from crest to trough. It's not. It's just the size from where it normally sits, the equilibrium position, to either the crest or the trough. Okay, so some other terms that you can't really draw a picture of on a wave. Frequency is the rate of oscillations, how many times it oscillates per second, and that term oscillations per second is given the units of hertz. Period is measured in seconds. It's the time between disturbances, and period is just given the capital T, and it is equal to 1 over frequency. And then velocity is how fast the wave is traveling, and velocity is only dependent on what the wave is traveling through. Okay, and so even though we have this equation, velocity equals frequency times wavelength, the frequency and wavelength can't change the velocity. The velocity is a constant for the medium it's traveling through. And what happens as the frequency of the wave goes up, the wavelength of the wave goes down. Okay, so frequency and wavelength are inversely related to each other. So we want to think about what does amplitude depend on? Amplitude depends on the amount of energy the wave is carrying. So it just depends on what caused the wave, so how much energy that imparted to the material. Wavelength and frequency are going to both kind of depend on how often like the disturbance happens. Okay, so how often like the material is shook back and forth. And velocity, how fast the wave travels, is only going to depend on what it's traveling through. Okay, and we'll see that in lab. Okay, so the speed of the wave depends on the density, the tension, like I've said before. When waves are being reflected, what happens to the wave when it's being reflected and when a wave encounters a boundary, what happens at that boundary depends on how different the media that they're going from and to, how different they are. Okay, so if they're very different, then you don't have very much transmitted. If they're very similar, you get a lot transmitted. When you do have wave reflection, the way the wave reflects depends on how the two densities of the two materials compare. Okay, so if I have a wave, let's say I have two different medium, and over here I have the more dense, and here I have less dense. Okay, the wave will come in like on this side, and if it's a significant density difference, only a little bit of the wave will go through, and the wave pulse on the more dense side, most of it will return back into where it came from. If I instead start in a less dense material and I go into more, and again there's a big difference between them, if the wave pulse comes in this way, okay, again only a little bit of the wave will be transmitted in, and most of the wave will return, but it will return inverted. So when you're going from less dense to more dense, the wave gets inverted on the way back. Okay. Now the frequency remains the same when the wave is transmitted. However, if velocity goes down, the wavelength goes down. Okay. So let me put a different kind of picture of that in. Where's my clear? Oh, here we go. Okay. So let me clear these out. So now let's say I have some waves coming in, and there's a boundary here, and the waves move very fast here, but move very slow there. Okay, when they get in, the frequency of the waves, which I can't draw in the picture, will actually remain the same. But because the waves move so much slower, they'll get piled up in the slow material where they're more drawn out. And if you can think about the wave moving backwards the other way, if you had waves close together, when they get into the fast material, again, the frequency stays the same, but they'll spread way out because now they can move faster. Waves can interfere with each other, and they can interfere with each other constructively or destructively. And so watch our video within a video here. If I can get it to play. I don't know why I'm having a hard time getting YouTube to play. And they must have done something goofy. All right, I'll play around with that. We'll get the video for you a different time. Okay. So anyways, with waves, if you have two waves, wave A and wave B, and they're headed towards each other, so actually these would be wave pulses, what happens is when they meet, you'll get a disturbance that's the size of A and B together, but then they just pass right through each other. So at some time later, you'll get them back, but now B is on this side moving away, and A is on this side moving away. That would be constructive interference. They added to get bigger. You can also have destructive interference. So destructive interference would be if I have wave A and B, and they're on opposite sides of each other, okay, and they're moving towards each other, then at some time when they come together, let's say if these two are perfectly the same size, shape, and everything else, you'll get nothing. And then at a later time, okay, not a much later time, these moves happen pretty quickly. Whoops, you'll have B over here and then A over there, and again they continue on their way. So destructive interference does not cancel out for all time, just at the time when they overlap. Okay, and again, we'll watch these YouTube things in class because I'm having a hard time watching them today, but we'll watch these, or okay, or maybe I'll put up links somewhere else. So when waves interfere, like when I was drawing the picture before, I was showing you examples of a single pulse. But the thing is if you send one pulse after another, after another, after another, so if you have just waves traveling down from opposite directions, what you can get is called a standing wave. So in a standing wave, the waves always hit so that you have a certain place where you always get destructive interference, and then you have some places where you always get constructive interference. So again, when I have a standing wave, I've got my material, and then from one end of the material is being sent a wave that's traveling down, okay? And from the other end, I'm going to do my best to draw this. Probably should just copy. There'll be another wave that's moving. Now I'm going to take this so I can actually move it. No, I just want the piece. That didn't work. Let's see if I can. Let's try it again. So I've got one wave here. Boy, it's really not cooperating today. All right, so I've got two waves traveling, and so as you see, as this wave travels, like right now, the two waves are completely out of phase with each other, and so there'd be a lot of destructive interference happening. And then as the waves come together, there'd be a lot of constructive interference happening. And then again, there'd be a lot of destructive interference happening. And then the wave travels along, and there'd be a lot of constructive interference happening. Now again, so as the waves go by each other, you get this constructive interference and destructive interference. And the overall effect of that happening is called a standing wave. Okay? So a standing wave happens, and what you end up happening is you have times when the wave is big like this, and then you have times when the wave is big like this. Okay? And everything in between. And what happens is, I didn't draw this best, you have these certain places on the wave that won't move at all. And those are called the nodes. Again, we'll see some examples of this in class. Okay? And then the places that vibrate back and forth the most, these are called the antinodes. Standing waves most often happen when you have the wave and it's traveling along the same material and getting reflected off either end. So then when it bounces back and comes back on itself, it's the same size wave. Now standing waves can only happen when the wavelength of the wave matches the size of the material. Because if it doesn't match the size of the material, you're not going to have this standing wave happen, because as they reflect back, they're not going to keep matching up in the same places. And so you won't get this nice set of nodes. So to get a standing wave, you have to have the frequency of your disturbance tuned to the proper thing to match it. But there's not just one frequency on each material that will work. Let's say if 80 hertz works, then 160 hertz will work too. It'll just make a standing wave that has a wavelength twice as short. And we'll see examples of this in class as well.